Hi, welcome to a window into programming and video games. I'm Daniel Espinosa from Nuevo Foundation. Let's get started. We interact with computer programs every day via many devices such as what we call computers, smartphones, and at the bus stop. Wait, the bus stop? Yeah. Have you seen these? They tell us when the next bus will arrive, and they use computer programs to do so. Computer programs have become such a normal part of our lives that we may not even realize we use them so much all the time. This brings us to the big question. I used to have it all the time, and I'm pretty sure many of you have had it too, which is, how does it all work? Let me tell you a little bit about me. I grew up playing video games, and I still play, and I remember enjoying them a lot, but always wondering, how do they work? How do they make this magic on the screen happen? I remember my older brothers telling me that it could be done with math. This didn't really answer my question. In fact, it sparked many more questions, like, how do you make math do that? Why math? And you can use math to make magic? When we're taught math at school, it can sometimes seem that it's a bunch of problems that we need to figure out solutions for. But I slowly realized, and I'm here to say, that math is really a tool, an incredibly useful one. And yes, a tool you can use to make magic. So, what is programming? Well, programming, or computer programming, is a way to instruct a computer to perform a task. We usually use code to do this. Now, there's a very key point, which is computers are not intelligent. We need to tell them what to do step by step in order for them to be able to do something. Let's see an example. Imagine your friend is offering to make you a drink, and you would like to have some tea. But she tells you she doesn't know how to make tea. So, you quickly explain that all she has to do is boil some water, put a tea bag in a cup, and pour the hot water in the cup. She then follows your instructions and offers you a great cup of tea. Seems easy enough, right? Now let's imagine you want a computer, maybe in the form of a robot, to make some tea. It turns out that this computer doesn't know how to make tea, just like your friend before you told her how. This is where it gets tricky. The first tea-making step you told your friend to do was to boil some water. Computers don't know how to boil water. You would have to outline very detailed step-by-step instructions to tell the computer how to boil water. For example, grab a pitcher of water. Lift the pitcher of water 6 inches. Align the spout of the pitcher with the glass. Then tilt the pitcher of water forwards by 40 degrees, wait 3 seconds, tilt the pitcher of water back by 40 degrees, then put the glass in the microwave, maybe wait till the water boils, and so on. These are so many steps, but we don't even have tea yet. This proves our point about computers not really being intelligent. Even though computers are not intelligent, there are key things that they are really good at. For example, they are extremely fast at calculating things and can work 24/7. Also, if we have instructions we've already written, and by instructions I mean a computer program, we can copy it and give it to another computer, or thousands of them, without having to write it again. So effectively, reusing instructions. What can programming be used for? Well, anything you've ever done on a computer or a phone has been made with, or basically is, a computer program. You can use programs to watch or make videos, write documents, and even TikTok. Yeah, some people came up with an idea like TikTok and decided to program it. Anything's possible. Now, in the world of STEM, science, technology, engineering, and mathematics, it is used to collect and process a lot of information, and to design and model things that people invent. And it is constantly being used in new ways every single day. There's another great reason to program. It's fun. It can be very interesting and satisfying as a hobby or a career. You can also make video games. I like this, and this is exactly what we'll be exploring today. So, let's talk a little bit about math. Many of my math students have asked me, Daniel, at school they want me to learn this and that math thing, but how is it useful for me? This is a valid and great question. Sometimes, when practicing math, it's very common to be solving a lot of problems to get better at understanding particular types of math problems. But we don't see how we can take those skills and use them in our life. I'll let you in on a little secret. It's all useful. And in this case, we will be looking at using math and logic to make games. Remember we talked about computer programs having to be very detailed and specific instructions? Well, math is precisely very specific and detailed. So it's the perfect tool for the job. An important concept we'll use today is the Cartesian coordinate system. Whoa, it seems like a complicated name, but I'm pretty sure you've seen one of these already. Also, if you haven't used one yet, look out for it in your math lessons and ask your teacher about it. It consists of two number lines, a horizontal one that we call the x-axis and a vertical one that we call the y-axis. So I've loaded up a website called Geogebra to help me set up an example. We can see our Cartesian coordinate system here. We'll call it a grid for short. We have our x-axis and our y-axis. The x-axis is horizontal, and the numbers increase as we go right and decrease as we go left. The y-axis is vertical, and the numbers increase as we go up and decrease as we go down. There are many things you can do on the coordinate system, or the grid, but let's name a few key things we're going to use today. One is placing points on specific coordinates, and two is moving points. By placing points and moving points is exactly how video games get their figures to move and do stuff. Let's see how to place points on the grid. First off, a point is placed on a set of coordinates. This is how a set of coordinates looks like. X, y. So this means the first number corresponds to the coordinate on the x-axis, and the second number corresponds to the coordinate on the y-axis. So for example, I can place point A. Point A would be on 3, 3. Let's see another example. Let's see how to put point A on coordinate 3, 2. So, first, the x-coordinate. So, 3, this means 1, 2, 3 on x, and then 2 on y. So, 1, 2. There we go. We've placed it on 3, 2. Let's see another example. How about we place it on 0, 4? So, 0 for the x-axis, which is here. And then 4 for the y-axis. 1, 2, 3, 4. Awesome. Let's see another one. How about minus 1, 1? So minus 1 on the x-axis would be over here. So let's bring A over here. And then 1 for the y-axis. That would be here. There we go. Minus 1, 1. Awesome. Let's see a quick other one. How about 2 minus 2? Okay, so 2 for the x-axis. So 1, 2, and then minus 2 for the y-axis. Minus 1 and minus 2. There we go. Awesome. Let's bring it closer to video games now. Say that we want to place a character on a certain part of the screen, and then we want the character to be able to walk. So, let's place point B here, and let's imagine that point B is a character. Now, let's say that x is its x coordinate and y is its y coordinate. So, if we move these, we can actually change the coordinates of B. So, if B is a character, then we can make her walk if we change the x coordinate, right? That is, if we assume that the x-axis is our floor. So, if we change the x value, 0.5, 1, 2, 3, you can see B start to move along. So that means she's walking. We can make her walk right and left. Cool. That's how video games do it. Alright, but how about jumping? Well, if we're going to jump, then we have to do something vertically, right? So we would have to change the y coordinate of point B, which is our character. So we can, if we change y and we increase it, for example, to 3, and then we decrease it, it's just as if our character B jumped. We can do it faster. Yep, that looks like a jump. What happens if we want to make a running jump? Let's say that we want character B to run and then jump over number 3. Okay, so we would have to make her run towards number 3 and then change her y coordinate to get her in the air and then move forward and then drop back down. Maybe she keeps on running a bit. Awesome. So if you imagine that sped up a little bit faster, then we've basically got a running video game character. So it may not seem like it at first, but computer and phone screens are like a version of the Cartesian coordinate system, so the grid. The difference is we use pixels as a grid. Keep this in mind for later. What if we're designing a game where we want the player to avoid an obstacle, to make it a little bit more challenging, maybe get to the other side and finish a level or something? We could create the obstacle by placing it on the coordinate system and change its coordinates constantly, so it can move up and down. So, let's say that player A is the character that we want to move, and B is the obstacle. So we could move B up and down by changing its y coordinate, right? Like this. So, what if we were to program it to go up and down and then repeat up and down and up and down? This would look something like this, right? Cool. It would be cool if we could go a little bit faster. So let's speed that up a little bit. Nice. Now, player A would have to run in order to avoid the obstacle. This is how video games do it. What would these types of actions look like if we were to program them? Well, we haven't seen code, but that doesn't matter. What matters is that we can detail the instructions. Once you have the instructions thought up, the coding becomes the easy part. So let's talk about the running jump we did before. What would be the instructions that we would have to program? Well, maybe something like place the character on coordinate 0, 0. Okay, so if her character is B, we can place her on 0, 0. Then something like increase the character's x coordinates by 1 unit every second. Okay, so every second she would go right on the x-axis. So 1, 2, 3, 4. Cool. We still don't have her jumping though. So how about after 2 seconds, increase the character's y coordinate by 1 for 2 seconds. Alright, so first 2 seconds, right? 1, 2. So 2 seconds have passed, and then we can increase the y coordinate by 1 and leave it there for 2 seconds. So 1, 2, remember the first one still, the second instruction is still active. And then we can do something like decrease the character's y coordinate by 1. Boom, there we have her landing. And then something like stop the character by not increasing her x coordinate anymore. And boom, there we go. She's walked to the right or ran to the right, and then she jumped, and then she landed. So this set of instructions is exactly the kind of thing we would program in a game. We could swap some of these instructions to happen when the player presses a button, like making the character jump when the jump button is pressed on a controller. There isn't really another way to describe this jump with the same level of detail without using math. For example, it isn't something I can describe by saying the character moves forward, then jumps high, but not too low either, and then lands on the other side. Sure, that's the general idea, but another person wouldn't be able to specify the jump exactly the same way we did. It's the same with a computer. It needs specific instructions. Now let's do the obstacle one. What would the instructions be for this one? Well, we could start with place the obstacle B on 4, 0. Okay, there we go. Then place the character A on 1, 0. Okay, there we go. Then increase B's Y coordinate by 0.5 every half second. Okay, so that would give us an increase like that. But how do we make it come down? Well, the next instruction could be when B's Y coordinate reaches 5, switch to decreasing it. Okay, so like that, and then we come back down. Cool, but I thought the obstacle had to go up and down. Yeah, we can do that by doing this. When B's Y coordinate reaches 0, repeat steps 3 to 5. Okay, so if we go up, 1, 2, 3, 4, we reach 5, we start decreasing the Y coordinate, and when we reach 0, it says repeat steps 3 to 5. So we do it all again. Okay, and then when we're done, we do it again. Okay, this seems to work. Yeah, this seems to work just like in the other example. Cool. We've got the working obstacle, and these are the instructions we use to do it. We're at the end of the video now, but let's talk about the key highlights. First, we learned that math is a tool. Also, that programming is a set of specific instructions. And we've also learned that math is the magic behind video games. Make sure that next time you play a video game, keep in mind what we've seen here today, because now you know a little bit more about it. Thanks for watching our video. If you can, please give us your feedback using this link. Thanks, and stay curious.